Next problem is a mechanism problem. Here's the starting material. Has a benzene ring in it. It has a tertiary alcohol. And this molecule was treated with acid, sulfuric acid. And the product looks like this. And the question is, mechanistically, how does that happen? All right? So before you press pause on the video, I just want to remind you some strategic hints about solving mechanism problems. See if you can relate the components of your starting compound to the components of the product. Number the atoms. That really helps to find the correspondence between where you're starting and where you need to get to. And then sort of think about what is changing in the course of this transformation. And then at that point, look at the reagent you have and ask yourself what a reasonable first step might be. So take a while to mull that over. Let's try to see if we can find where the atoms are in the product. Maybe if we start here at this carbon, it might be reasonable to guess that we come to here. And then if I number around the ring 2, 3, 4, perhaps we would have something of this type. Let's do a reality check. Look at carbon 4. Carbon 4 has 2 methyls on it. And over here, there's 2 methyls attached to carbon 4, so that's reassuring. Carbon 3 has 1 methyl on it, and there's a methyl over there, so maybe this is a reasonable guess. Don't forget about the hydrogens, though. So if we look over here at carbon 4, there's a hydrogen. And that hydrogen is missing over here, so that hydrogen must somehow go away. And then the other issue is that at carbon 3, there's a hydroxyl group, whereas over here at carbon 3, there's not a hydroxyl group. In fact, there is a hydrogen at that position. And then in terms of what is the key bond that we would need to make during the course of this mechanism, you certainly have noticed that in this starting material, there's the benzene ring, but that's the only ring there is, whereas in the product that we're trying to get to, there's a second ring. So with that in mind, give the mechanism a try. To get started, we might identify something that could happen in the presence of an acid. So here is sulfuric acid. And a reasonable place to start might be protonation of this alcohol. So if we protonate there, that makes the OH group into a much better leaving group. Let's keep the numbers on the molecule here. So here's carbon 1, carbon 2, carbon 3, carbon 4. So at this point, and feel free to pause the video at any point once you kind of get the hang of what to do, the leaving group could leave, and that's going to generate a carbocation. And now we start to get to the point where maybe we can think about making a carbon-carbon bond via a Friedel-Crafts type of process. The problem is that we don't want to make a new bond between this carbon right here and carbon 3, which is where the positive charge is at this point. What we really need is a new bond between this carbon of the benzene ring and carbon 4. So somehow we need to go from an intermediate that has a positive charge on carbon 3 to one that has a positive charge on carbon 4. So there may be more than one way to achieve that, but one possible way would involve a carbocation rearrangement. So see if you can think about how that would look. But let's not forget about the hydrogen that is over here on carbon 4. If that hydride were to migrate from carbon 4 to carbon 3 in this way, that would be a 1,2 hydride shift. And you might ask, well, why should that happen? I already have a tertiary carbocation. Well, let's look at the carbocation that results from that migration. So here is the hydrogen that moved, and the carbocation that results from that hydride shift, it's also a tertiary carbocation. So if you think about the energetics of that, energetically it's kind of even trade. Maybe it's easier for this carbocation than for this one to cyclize to make the appropriate 6-membered ring. Or you might think of some other way that one could generate this sort of carbocation. For instance, instead of a 1,2 hydride shift, maybe an elimination to form an alkene, and then under the acidic reaction conditions, a protonation of that alkene to give the appropriate carbocation. So there are alternatives to this hydride transfer mechanism, but this is one possible way of getting to the product. So here we are. Friedel-Crafts alkylation. So if you want to try to write that, if you didn't get to the product yet, think about a Friedel-Crafts alkylation reaction of this carbocation. It will be an intramolecular Friedel-Crafts alkylation. Let's include this hydrogen here. We're going to use the pi system of the benzene ring to make a bond to carbon number 4. Let's keep the numbers on here, 1, 2, 3, 4. And then maybe let's just keep going here, 5 and 6. So we're going to make a new bond between 5 and 4, and that's going to close this 6-membered ring. Anytime you make a ring, just verify that you have the right number of atoms in that ring. It's easy to lose a carbon or some other atom. So that looks good. On carbon 4, oops, there's no double bond there, sorry about that. On carbon 4, there are 2 methyl groups. On carbon 3, there's 1 methyl group. On carbon 5, there's a hydrogen. And on carbon 6, there will now be a positive charge. So we're almost there. We're almost done. We just have to do the second part of electrophilic aromatic substitution. Namely, we look in this cyclohexadienal cation ring. We find the carbon that is sp3 hybridized. There it is. And then we know that we need to remove the proton attached to that carbon. What base am I going to use under these conditions? Perhaps the best base I have is the conjugate base of sulfuric acid. So there it is. Use it to remove this proton, restore the aromatic ring of this left-hand ring, and there we are at the product. So remember the mechanistic, the guiding strategy for doing mechanism problems. Before you actually start pushing any arrows, take some time to analyze the starting material versus the product. Orient yourself in terms of what bonds need to be broken, what bonds need to be made, what are the changes, the important changes that are occurring, and only then should you start trying to actually indicate the reaction pathway using the arrow formalism.